Hello? Okay, great. Do you have any questions so far? Any questions? Say again. No, until the last chapter, the central video. From the beginning to the central video. Okay? That makes sense. Okay, yes, that's true. Is there any questions? Any questions so far, everybody? Any questions? So it seems that everything is fine for you, right? Is that correct? Is that true, everybody? You're not clear about the population and this sample. Okay, sure. Definitely, I can explain about that. Think about it this way. Suppose that you want to learn about, let's say, okay, you want to learn, the number of people who are infected by COVID-19. All right, that is what you want to do. Want to get. So you want to get the number of people living in our country infected by COVID-19. So what is the population in this case? What is the population? The population would be the set of all the people living in our country, right? So I would say the whole country. Okay, whole country. And can you get the information about the whole country? Definitely cannot get it, right? And, even the government cannot get it. The better way to get it is to get just a sample. So I'm going to select some people, right? Some people, and tries to estimate it, and tries to count the number of people infected by COVID-19 in that sample, only in that sample, okay, in that set. And that set is called a sample. So this is the sample. And this is called the population, the whole thing. So the population is a bigger set, and the sample is just a part of it. Understand? There is only one population, all right, because there is only one country here. Understand? But how many samples are there? There are lots of samples. I get one sample, you get your sample, all right? So every time you get it, you get another sample, correct? So this set is a sample, that set is a sample, this is also a sample. Okay, so there are many samples. And from the population, I can count a lot of things. I can count the number of people who are infected by the COVID-19. I can compute the proportion, right? Understand? And then, so there are a lot of things that I can do, all right? And for example, I can do the same thing, a similar thing for that set, but only for within that sample, all right? Understand? And the value you get from the population is called the parameter. For example, I can get the mean value, I can get the variance, okay? I can get the median, all right? I can get the standard deviation and so on. From the sample, from each sample, I can get a similar thing. I can get the average value, but I will call it the sample mean to indicate that it is obtained by using the sample, not the whole population. The mean here is the population mean. The median here is the population median. The variance here is the population variance. Okay. So we usually use the H bar to indicate to denote the sample mean, and we usually use n or sometimes mu to denote the population mean. For the variance, we use V. For the standard deviation, we use SD. Right? Or for the notation, you get sigma squared. For the standard deviation, we use sigma for that. And if you want to get, if you want to denote the sample variance, we use the notation n squared, and S should be for the sample standard deviation. Is that all clear, everybody? Is that clear? So you can get a sample and you can compute a lot of things with a sample. And if you get a very good sample, that will give you some good approximations for the parameters, all right? But if the sample is bad, then you know the information you obtain cannot be used to approximate the parameters. Is there any questions so far? Is that clear? Is there any other questions? Any other questions? May I move on, everybody? Okay, let's go back to this. I think last time we already talked about the confidence interval for the mean value. And if you remember, the formula should be m equals x bar plus or minus the alpha over 2 times sigma over the square root of n. This means, remember that, this means that the x bar minus n is less than or is less than that value, right? The alpha over 2 times sigma over the square root of n, all right? Okay. But sometimes you want to get, and this is epsilon, of course. And sometimes you want to get just one you know, 1 bound instead of two bounds like this one. This inequality gives you 2 bounds, right? A lower bound and an upper bound. Makes sense? But sometimes you only want to get 1 bound, an upper bound, for example, or a lower bound, right? How about that? What if you want to get this one bound? Suppose that you want m to be less than x bar plus epsilon. That's everything you need. You don't need this. You don't need something like this. You don't need this one. You don't need it. You don't need a low bound for that. You only need to have another bound for the mean value. In alternative this inequality, you can get the equivalent inequality x bar minus m is greater than minus epsilon. Okay, and you can use similar arguments to see that gamma is the probability that x bar minus m is greater than minus epsilon, and divide this one by sigma over the square root of n, sigma over the square root of n, correct? And then you can see that this is z, right? And this is simply c, all right? And if this gamma and this minus c, this minus c, so you come up with this one. This is gamma, and this area is alpha, right? And this is obviously minus z alpha, all right? Okay, so you see that you have only one tail in this case, the left tail instead of the right tail. Makes sense? You get this one, and because of this, you can see that the epsilon you can obtain should be let me see if I get something wrong there. Yeah. So the epsilon you obtain should be, what is that? Should be that one, right? So the epsilon you obtain should be C alpha. Understand? Times sigma over the square root of n, because minus C alpha equals minus C, which is minus epsilon over sigma over the square root of n. That's why you obtain this one. Okay, so you get the following confidence interval for the mean value, and this one is called a right-sided. Okay, because you have an upper bound for that. Mu less than or equals to mu hat. Sometimes we can use the x bar for that. X bar for the mu hat plus z alpha times sigma over the square root of n. All right, and you can also get a left-sided confidence interval for the mean value. Okay, I call it this one the right-sided, and this going to be the left-sided. Is that all clear, everybody? Is that clear? May I move on? May I move on? What is hat? Well, hat is just a notation. If you don't like it, you can replace that one by x bar. You can think about it this way. Okay? Does it help for you? Okay. All right, let's go back to our problem here. In auto racing, a pit stop is where a racing vehicle stops for new tires, fuel repairs, and other mechanical adjustments. The efficiency of a pit crew that makes the adjustments can affect the outcome of a race. A random sample of 32 pit stop times has a sample mean of 12.9 seconds. Assume that the population distribution is normal and the population standard deviation is 0.19 seconds. Construct an upper 130-95% confidence interval for the population mean. Can you do that? Think about that for a minute and tell me your answer, please. Just type in the answer in the task box, please. Did you get the answer, everybody? Did you get the answer? No? Well, I want to remind you what we can do with the problems last time. I think this is what we did last time, right? I hope that you still remember that. Correct? This is what we learned last time. Am I right? So you come up with a two-sided confidence interval, 99% confidence interval for the mid-bit stop time, and you get the H bar plus or minus the Z value times sigma over the square root of n, right? And then you get this one, all right? How about this one? How about this problem? You want to get a one-sided upper confidence interval, right? So it should be you want something like m is less than h bar plus z alpha times sigma over the square root of n. Makes sense? All right? So m should be less than x bar is the average value in this case, and the sample mean is 12.9 plus z alpha times sigma. Sigma is 0.19, and n, the sample size is 32. All right, so you get 32. It is remaining to determine the value of z alpha. In this case, the confidence level is 95%. So you get 95%, right? Z alpha is the point such that the areas to the right is alpha, right? So that is 5% here, because this is 95%. Okay, and this point is Z 0.05, and you can get it very quickly using the table or software. Okay, and the answer it should be the answer in this case is 1.64. All right, so I put 1.64 over there, and I get the answer. Is there any questions so far, everybody? Quite simple, right? Is that clear? All right. May I move on? Okay. Well, in the first case, we already learned the first case. I just give you a reminder. You get x1, then x2, and then xn. They are independent, and they follow the same number distribution with the mean and the variance sigma square. Here, the value m is a null, and that is what you are looking for. But the value sigma square is null. And because you know that value sigma square, you can get this value, right? And you can get the answer. All right. Now we move to the second case in which they are still independent. Okay. And they have the same normal distribution, the same mean, the same variance. Okay. And m is still what you are looking for, and you don't know it. But the problem here is that sigma squared is unknown. Okay, you don't know that value of sigma squared. And if you don't know it, then you cannot get the value of sigma. You cannot get it, and then you cannot use this formula. And the main idea of the method is you have gamma equals the probability that x bar minus m is less than epsilon. And in order to deal with it, you have to know the distribution of x bar. If you don't know the distribution of x bar, then you cannot get the probability, and there is no ways to deal with it. Okay, but we knew that if they have normal distribution, then x bar minus m over sigma over the square root n, that would follow the standard normal distribution. However, now you don't know sigma, right? So it is very natural to approximate sigma by S, where sigma is the population standard deviation and S is the sample standard deviation. Then you can come up with the fraction x bar minus m over S over the square root of n. Well, we don't really expect that the fraction follows the standard normal distribution because you already changed the value of sigma by S. Okay, by the way, I'm going to denote this one by T. Okay, so this T, this random variable T does not follow the standard normal distribution. And if you don't know this distribution, then we cannot get what we want here, right? Luckily, there was a statistician who was successful to prove to achieve the distribution of the random variable T, and the distribution is the T distribution with degree of freedom and -1. All right, is that all clear, everybody? Okay, all right. Now I want to give you the graph of the standard normal distribution and the T distribution, so that you can get some idea about it. There is a single standard normal distribution. There is only one standard normal distribution, but there are several. There are many standard distribution, or you can call it the T distribution. Okay, you can call it a standard distribution or T distribution. The T distribution with the degree of freedom smaller than 30 is the looks like the green curve, and the T distribution with the degree of freedom greater than about 30 or greater than 30 looks like the red one. And when the degree of freedom is greater and greater, you can come up with some distribution closer and closer to the standard normal distribution. Okay, so if the degree of freedom goes to infinity, the standard distribution will be closer and closer to the standard normal distribution. Makes sense? That's why if the degree of freedom is big enough, we can use the standard normal distribution to approximate the standard distribution. All right. Now let's go back to this. Because we already knew the distribution of the T, then we can use the similar approach to get what we want. Gamma is the probability that x bar minus m is less than epsilon. And then we get the probability that x bar minus m over S over the square root of n less than epsilon over S over the square root of n. And and that is the probability that the absolute value of t is less than. We have the right hand side here. That is C. Okay, that is C. And this is what you get. Okay. So this t is from minus C to C, and this is gamma, and alpha is 1 minus gamma, and we get this the area of the two tails is alpha, and this is alpha over 2. That is alpha over 2. Okay, and then yeah, using the distribution. Okay, now you see that the degree of freedom is n minus 1. That was proved. We just use it. Okay, and we have the degree of freedom here is n minus 1. Then you can determine the value C, which is the T alpha over 2. T alpha over 2 is the point such that the areas to the right is alpha over 2. Is that all clear, everybody? Is that clear? That is for a two-sided confidence interval. All right. So for a two-sided confidence interval, you can see that C is T alpha over 2, and that is epsilon over sigma. S over the square root of n. And then you can solve for S to get T alpha over 2 times S over the square root of n. That's it. Okay. Is there any questions so far, everybody? So n equals x bar plus or minus T alpha over 2 times S over the square root of n. Any questions so far, everyone? Is it okay? Is that clear, everyone? Is that all clear? Okay. All right. Let's move on to the example. Eleven randomly selected automobiles were stopped, and the tread depth of the right front tire was measured. The sample mean was 0.32 inch. The sample standard deviation was 0.08 inch. Find the 95% confidence interval of the mean depth and just the mean depth, and then assume that the variable is approximately normally distributed. All right. Can you do that? So what is n? N in this case is 11. 0.32 is the sample mean, right? And 0.08 is the sample standard deviation. That is the sample, so it must be S, not sigma. And 95% is gap, the confidence level. So n is x bar plus or minus the t value times s over the square root n. Okay, what is x bar? X bar in this case is 0.32 plus or minus the t value. And s is 0.08 and n is simply 11. So you can get that confidence interval as long as you know the value of t. And what is t, by the way? You need to have a look at the confidence level, which is 95%. So alpha is 1 minus 0.95, and you get 0.05. Okay, and this is going to be 0.025 because you have to divide alpha by 2. Get that? And what is this term? This point. This is the t alpha over 2, so 0.025. So t is the point such that the areas to the right is 0.025. Okay, and so this is going to be 0.025. And how can you get that? How can you get it? How can you get the t value? In order to do that, you need to you can use the table or the software to get it. For a table, if you use a table, you have to be careful. You need to make sure that you use the correct table. So I'm going to use the table this time. So you can have a look at the table. This is, first of all, is the t distribution table. All right. Second, you need to have a look at the degree of freedom. The degree of freedom is this column, and you get the degree of freedom 10 because n is 11, so the degree of freedom is n-1, which is 10. And the areas to the right is 0.025. 0.025 is this one. So I get the point 2.228. Okay, and I get 2.228 here. Is that clear, everybody? If you use software, you can use Qt for that. All right, so you get 0.025. Maybe let me copy that you can get it quickly. So Qt, so 25, degree of freedom is 10. We want to get the right tail, so we get this point. Okay, so you get 2.228139 for the more accurate value. All right, any questions so far, everybody? Is that all clear? All right, okay. Let's consider the next example. Five independent measurements of the point of inflammation of the soil gave the values in degree Fahrenheit: 144, 147, 146, 144, 142. Assuming normality, determine a 90% confidence interval for the mean. Can you try the problem? Okay, get the answer, everybody? Yeah, great. Just for your information, the average value is 144.6, and the sample standard deviation is 3.8. Okay. Please tell me yes. All right, let's see. First of all, the X bar should be 144 plus 142 divided by 5, right? And N squared is 144. This is going to be 144.6. And S squared is 144 minus 144.6 square. You need to compute the square of the derivations. 142 minus 144.6 all square divided by the degree of freedom, which is 5 minus 1. And you should get 3.8 for that. Then M is X bar plus or minus T alpha over 2 times S over the square root of N. Or I may say x bar plus or minus T alpha over 2 times the square root of S squared over N, okay? And that is 144.6 plus or minus the T value. The square root of S squared, that is 3.8. And N is 5, right? And what is that number, by the way? We are dealing with the standard distribution. The degree of freedom is 4. So and the confidence level is 99%. It is 99% here. And is 0.01. You get T 0.01. Okay, so the areas to the right is 0.01 and the degree of freedom is 4. I go back to the table. The degree of freedom is 4 and alpha, the area is 0.01. So the value you get is 3.747. Or you can use the software for that. So it is 3.747. Okay, is that all clear, everybody? Oh, thanks, Juan. That is correct. The formula is correct. That is the sample values. Is that clear, everyone? And remember to do the calculations. Do not, you need to do the calculation for this to get a final answer. Okay. And if you do the calculations, you should get, I would say, 1 is 4. It is 3.2665. And then you can say that n belongs to the interval. Why is that? 141, 13335, and 147. I think 147, 8665. Do you understand? Any questions? Is it okay? Okay, let's have a break. Then after that, I will move to the case when you don't really know the distribution, right? For now, you know the distribution. There are 2 cases here. You know the distribution of the observations, right? That is normal distribution with the same values. And there are 2 cases here. There are 2 subcases. You may know the sigma square or you don't know it. All right. The third case is that x1, xn, they are ID, but you don't know the mean. You don't, okay, and you don't know the distribution. You don't know it. All you know is that they have the same distribution. That's all. And the mean with the same mean, right? The same mean and the same values. The point is that you don't know n, right? You don't know n. You don't know the value of n. You don't know this one. This is a no. And for sigma square, you may know it or you may not know it. It doesn't really matter. Okay. All right, let's have a break. And then after that, I will talk about this case. Hello, can you hear me? All right, let's continue with the case when you don't know the distributions, okay? If you don't know the distribution, how can we get a confidence interval? Well, if you want to get a confidence interval, you need to know, again, you need to know the distribution of x bar. But if you don't know the distribution of xi, what is the distribution of x bar? Or let's say, what is the distribution of x bar minus m over sigma over the square root of n? What is that? You don't know for sure. You don't know for sure. But we know that if n is big enough, that is approximately for the distribution is approximately the standard number distribution, right? So you can that is the central limit theorem. So you can use the central limit theorem in this case to solve the problem, right? When n is big enough. You may ask a question, what if n is not big enough? Well, can we get that? Yes, we can. We can get a confidence interval in that case. But we're not going to study that in the course, all right? You may try that with your project, all right? But we will not learn the method, all right? If you do the project and you need my support about that, then I will talk about that to the groups. But we're not going to learn that. But there are several methods that you can use. Basically, they are non-parametric method, right? So back to our case in which we had the assumption that n is big enough. That is a very important assumption, okay? Well, you may say, how do you know that n is big enough? How do you know that? It depends on the original distribution, all right? If you get a heavily skewed distribution like this, then n has to be quite big. Let's say 1,000. All right. If you have something like this, then I think 50 or 100 should be okay for you. All right. Okay. But if the distribution is heavily skewed, then you need more observations. Is that clear? All right. So there is no fixed value that you can use to determine to decide if it is a big or small. In the exam, we have we assume that if n is greater than 30, we assume that is big enough. If n is less than 30, we assume that is not big enough. All right. But please keep in mind that it is only for the exam, not for reality. Understand? Okay. There is a reason for that. When n is greater than 30, the standard distribution is close to the standard number distribution. All right. So we can and we can use the central limit theorem in that case. But it's not. Remember that it is not a magic number. All right, let's go back to this. What if you don't know sigma? What if sigma is a no? If sigma is a no, then you can approximate sigma by S, and then you can get that confidence interval. All right, you can get, you can use this one. Let's say Z is still the X bar minus M over S over the square root of n that approximately follow the standard norm distribution. Okay, is there any questions so far, everybody? Is that all clear? May I move on? Is this all right? Okay. So as long as you get this response, you can use similar arguments to get an approximate confidence interval. So I'm going to give you the formula for that. If xi follow the same normal distribution and they are independent, then and n is large enough, then you get this confidence, this formula for the confidence interval. Okay. Is there any questions? That's okay, right? Okay. Let's try the following example. Oh, by the way, there is a video I want to share with you. Let me see if I can share the video. do you see the video I'm sharing with you? Can you see it? Can you see it? Hello, can you see it? All right. And please tell me if you can hear the audio. All right. Can you hear it? I just stop it, but can you hear it? Okay. So if you have a problem with the sound, please let me know.
It's 112 grams, 40-gram sample standard deviation. What is the probability that the mean weight of all 200,000 apples is in 100 and 124 grams? So let's think about what they're asking. So there's some distribution of all of the weights of all 200,000 apples, or more than, don't even know how many apples, just a huge number. There's some population distribution of something like that. We'll have a weight, has a weight. We don't know what that mean weight is. And it also has a population standard deviation of the population. Well, right here, the population standard deviation. Both of these are parameters that we do not know of the entire population. Now, we know from our experience with the last few videos that you can repeatedly take samples, or if you kind of visualize, repeatedly take samples of a certain size. In this video, we're going to focus on sample size of 36. And you keep taking the means of those sample size. You plot the free, eventually get something called sampling of the sample mean. That would might look something like this. I'll try to more. It is going to be pretty close to a normal distribution. Pretty close to normal distribution. It's going to have some. Has some show that this is. And we know that the mean of the sampling distribution is all of your vector distribution actually going population. Here, it also has some standard deviation. Above the mean is a standard deviation. Below the mean right over there, specify that by the standard deviation of the sampling distribution. And we know that this can be given or approximately fairly large samples. This gets a pretty good indicator of correction factors. But this is going to be our population standard deviation. Our population standard deviation divided by the square root. So this is the last two videos. Divided by the square root of the number of samples we have when we calculate the distribution. 36 samples. Sampling distribution. Right. 4 and equal 6. For each of our sample buckets or baskets to have 36 items. That is essentially each of those pieces is a sample from this distribution. These are the samples that fit the thing that we're using to calculate the samples are samples. So if they use the things that we're used to calculating them are the samples from that. Hopefully this is too confusing. Anyway, this distribution's standard deviation is going to be the standard deviation, this population standard deviation, divided by 6. We still don't know this. We still don't know this parameter up here. Now, with that said, let's refocus on what they're actually asking us. They want to know the probability that the weight of all 200,000 apples. Well, the mean weight of all 200,000 apples is that right there. And they want to know what is the probability that it is between 100 and 100 grams. So they're actually asking us 100 and if something is between 100 and 100 grams, it is within 12 of our sample mean, right? That's all they're saying. What is the probability that this thing is 12 of our sample? Less than 12, if you're 12 less, you're going to get to 100. If you're 12 more, you're going to get to 4. This, what they're asking us is, what is the probability? What is the probability that our population mean, this parameter, unknown parameter, is within 12, it's within 12 of the mean of our one sample, of our one sample. Now, if I told you that I'm within 5 feet of you, then that also means that you're within 5 feet of me. The exact same thing. Exact same thing is the probability that the sample mean is within 12 of the actual mean. And I really want you to make this make sense. If I said, what's the probability that I'm either 5, if I'm either 5 behind you or 5 ahead of you, that's the same thing as the probability that either 5 behind me or 5 behind you. That this is asking, what's the probability that we're 12 apart? Or that what's the probability that I am within 12 feet of you? Probability, what is the probability that you're within 12 feet of me? They're asking the exact same thing. When you phrase it this way, it might dawn on you that you might be able to use the sample. There's some unknown mean here, which is the same thing as this value right here. So this thing, let me make it very clear, this is also the same thing, because this value and this value exactly the same thing. Exactly. What is the probability that our one sample mean is within 12 of the actual mean of the sampling distribution? So we're just saying, what's the probability that that one sample mean we have is within 12 of this actual sampling mean? At this point, your brain should be thinking that, gee, if I can figure out how many standard deviations that is, how many standard deviations is the way that it is, I can make this table actually. No, that's exactly what we do. But there's one slight complication. We don't know the actual standard deviation. We know that it's this thing right over here divided by 6. But we don't know this thing. So what we're going to do is get our best estimate of this. We need a good estimator for the actual population standard deviation. Well, what's our best estimate of that? It's going to be our sample standard deviation. We sampled 36 things. We get a sample distribution of 40. So we have a sample distribution of we have a sample, let me write this way. It's going to be approximately to our sample distribution, our sample standard deviation, which we got to be 40. So we just found the mean of our 36 apples, the weight is 112 grams, and we found the square distance from each of the apples' weights to this, the average of those. Pick up average divided by n minus 1. We learned all of this 3 years ago. And then we just put that. This gave us the sample standard deviation. Here's our best estimator. Our best estimator for that. Our best estimator for this thing right here is going to be our sample standard deviation divided by 6. 46. Let's get our calculator out. So we have 40 divided by 6. We have 6.6. I'll just write down 6.67. Right here is 6.67. So our best estimate of the standard deviation of the sample distribution of the sample mean is 6.67. So this distance right here, 6.67. So how many standard deviations is 12 if you look at this distribution right over here? We just divide 12 by 6.67. Right. Calculator back up. We have 12. I'll just divide by that. 12 divided by answer, just use the last answer we got. That gives 1.8 exactly. We got 12. So this is analogous to saying what is the probability? What is the probability that our one sample is within 1.8 standard deviations? Let me write this one. Standard deviations of the sample, 1.8 of these, of our actual of our actual mean of our sample. Literally just asking that. Look at this distribution up here. Within 1.8 standard deviations, one standard deviation, another 0.8, maybe get us right about there. And we're within 1.8 above and 1.8 below. 1.8 below, so this is 1.8 standard deviations above the mean. This is 1.8 below the mean. We're just going to say, what's the probability when we just took this one sample of 36 apples, we lie in this space over here? We lie in this space. And to figure this out, what I'm going to do is I'm going to use our Z table to figure out essentially this space over here, just probably 12 above it, and then we can just double it. Let's go to our Z table. This is the probability of between the mean, 1.8 standard above the mean. Just go straight to your Z table. 1.8 is here. This is right over here. Now you get this 0.9641 number, but be very careful. 0.9641 number, that gives you, so if I draw normal distribution, if I draw normal distribution back, this is our mean. This 0.9641 number tells us the probability that we are less than 1.8 standard deviation above. This is giving us this entire area. This entire area right over there. So if I want just this area right here, what I need to do is from this value, from this 0.9641, I need to subtract this probability that you're directly less than this. That is this probability that you're less than the mean plus 0 standard deviation. This value right here is 0.50. This whole area that I just showed there is 0.9641. So this area right over here, is going to be 0.9641 minus 5. 0.4641. This area right here, just look this in magenta, just there and there, is 0.4641. 0.4641. 0.4641. And if I want this entire area, I just double it. If I want to do this as well, I just have to double that. Calculator out. Calculators. 0.4641 times 2 to 92.928. This whole area right over here. 2.92. So we did something, the probability that answering right here, the probability that our sample mean just happens to be within 1.8 standard deviations. Remember, that was 1.8 standard deviations of the sample mean from the actual mean is 0.9282. There's a 92.82% chance. That's also saying that there's a 92.82% chance that the actual mean is within 12 of our measured sample. And that is neat because for the first time ever, we started with very little information. We just started with a little sample. We're able to get as much information about that sample as possible. We can now say that there's a 92.82% chance that the actual mean is within 12 of the mean we measured. The actual mean is within 112 or between 100 and 124. Or that we're 92.82% confident that the actual mean is in the range. I think that's pretty good.
Okay. This is just another way to solve the problem. Quite similar to the one that we just did, right? And but I want you to, because some of you may have a problem with using the table. I'm not sure, but some of you use another table. So I want you guys to have a look at this, and hopefully it is useful for you. And it can give you, because we just get the confidence interval, right? And then we use the way of computing the standard score. You standardize the random variable, right? And you use the and you use the normal distribution. This is a very similar way, very similar thing. All right, and hopefully you understand that. And if you have any questions, please feel free to ask. Okay. Now I want to go back to the slide. Do you have any questions so far, everybody? By the way. That is just just review of what we just learned. And now I want to go back to this example in which we use the concept of the central limit theorem, all right, to achieve a confidence interval for the mean value. So let's say a random sample of 110 lighting flashes in a region resulted in a sample average greater equal duration of 0.81 second and a sample standard deviation 0.34 seconds. Calculate a 99% two-sided confidence interval for the true average equal duration. Can you think about that for just 1 minute, and then I will go over the problem. The formula is right here. Just think about that. Can you get the answer? Okay, so let's go back to this problem. You see that suppose that M is the true average equal duration, that is M, and you can approximate it by the average value, H bar, right? H bar in this case is 0.81 plus or minus, okay, the Z value. In this case, you don't know the distribution. Is it normal? You don't know. Is it normal or not? You don't really know. You don't even know the distribution of the observations. But because the sample size is quite can be considered big, so you can use the formula. And by the way, we don't have the population standard deviation, so I will use the population standard deviation instead. Anyway, this is just the approximation. That's why we can use sigma or S. If you know sigma, you should use sigma. If you know S, if you don't know sigma, you can use S for that. Divided by the square root of n. Okay, and I use this notation because it's just an approximate confidence interval. It is not the exact confidence interval. Up here, you have the exact confidence interval. It is an exact confidence interval. But the one we have here is just an approximate confidence interval. All right. All right. So you get M. H bar is 0.81 plus or minus the Z value. The value S is 0.34 and N is 110. Concerning the Z value, I need to have a look at the graph, right? And I use the confidence level, 99%. This is 99% here, and you come up with the value right there. This is alpha equals 1 minus 0.99, and you get 0.01, and you get 0.005, and this is 0.005. So the point right here, the value 0.005, you can use the table of that, get 2.58. 2.58. Okay, and then you can get then you can get it. Makes sense? Is that all clear? Okay. All right. Now I want to move to the last case in this chapter. We can we have this one. We can do this one for all cases. So it seems that this is a very powerful tool, right? Because we can do it for all cases, for all distributions, correct? So can I just use, so instead of using, in this problem, let's say I have 100 observations. Not 5, but I have 100 observations here. And they follow a normal distribution. Should I use this one? Should I use this method or the distribution method? Which one should I use? You know, if the observations follow a normal distribution, then we should use the t-distribution, because the t-distribution gives you the exact confidence interval, right? And the one we have here It's just the approximate confidence interval. It is not the exact confidence interval, in a sense. So yeah, if you want, if you have the observations following the normal distribution, then you should use the distribution, even if the sum size is big. All right. Okay, and then I want to apply the method to the case that all the xi follow the same Bernoulli distribution, like that. Okay, it means that xi could be 1 or 0 with a probability p q. Okay, and then you can see that the mean value is p. Remember that, right? And the variance sigma square is the variance of xi, and that is p times q. Okay, you can approximate p by the p hat. That is the sample proportion. So I call p the population. I will call p the population proportion, and p hat will be called a sample proportion. Do you understand? Okay, and then I can approximate pq by p hat q hat, correct? And this is the sample variance, right? Okay, so you can go back to the let's say this is basically the S square. Okay, this is the S square. So I can get the confidence interval m equal x bar plus or minus the alpha over 2 times the square root of the variance s squared over n. And if I replace n by p, x bar by p hat, this is x bar because that is the sample mean, right? The sample mean of the sample proportion. That p hat plus or minus the alpha over 2 times the square root of p hat q hat over n. And then you get an approximate confidence interval for the proportion. Okay? Is that clear? That is okay, right? You can also get a one-sided confidence interval for the proportion. This is the one that I just mentioned. Okay, so we have a similar result. And remember that you should use Z alpha instead of Z alpha over 2 when you want to get a one-sided confidence back. Okay. All right. In this case, all right. Is that clear, everybody? That's good, right? Let's consider the following example. An article reported that in 45 trials in a particular lab, 16 resulted in ignition of a particular type of substrate by a lattice cigarette. Let P denote the long-run proportion of such trials that would result in ignition. Find a point estimate for P and the confidence interval for P with a confidence level of about 95%. What do you think? In this problem, you need to, you get P, right? And then P hat plus or minus the value. This is a two-sided confidence interval. If they mention nothing, then it must be a two-sided confidence interval. The alpha over 2 times P hat Q hat over N. The P hat is 45, no, I mean 16 over 45, right? So you get 16 over 45 plus or minus the Z value. 16 over 45 times 1 minus 16 over 45 divided by N, which is 45 here. How about the Z value? The confidence level is 95%. So it must be 95% here. That is gamma. Alpha is 1 minus gamma, so you get 0.05. The area of the two tails is 0.05. And because it is symmetric, so each tail should be 0.025. That's it. Okay? Is that clear? And you can use the tables to get the value 1.96. 1.96. All right? Is that all clear, everybody? Is that all clear? Is this okay? So that is basically what we have learned so far in this chapter, right? And we can see that there are several cases here. The distributions are normal or not. If the distributions are normal and you know the population variance, then the error is this value. If you don't know it, then this is the one that you use. You need to use the t-distribution. If the distributions if you don't know the distribution of the observations, then you need the assumptions that n is big. All right. In the exam, let's say n is greater than 30, it's big for you. Then we we have the error, is this one. You know, you get the this notation because that is an approximation. It is approximation. It is an approximate confidence interval, right? It is not the exact confidence interval. Okay, and in particular, you can apply it for the proportion. Okay, so for the proportion, then you get the error, which is the z alpha over 2 times the square root of p hat of n. Okay. I want to tell you something a little bit more about the notations. We get sigma. That is, what is sigma? Sigma is called the population standard deviation. Okay, and S is called a sample standard deviation. Okay, all right. How about sigma over the square root of n, which is the mean value of x bar? This is called the population standard error. You call it the standard error. So the standard error is simply the standard deviation. I'm sorry, this is standard deviation. Yeah. Okay. So standard deviation of x bar. So the population standard error is simply the standard deviation of the sample mean. Okay. And you get S over the square root of n. That is called an estimated standard error. So, or let's say this a sample standard error. Okay, or you can sometimes you call it the estimated. Is that all clear, everybody? Is that clear? Okay, so this is the SD. We call it SD, and this is SE. All right. May I move on, everybody? Is that clear? Is that all clear, everybody? Okay. Now I want to move to the next chapter. I don't think that we have enough time to go over the whole thing. So I think I just have enough time to go over just the beginning of the chapter. Let's see. Okay, now I will give you a brief introduction about the hypothesis testing. So the next chapter will be about hypothesis testing for one sample. what is this about? Okay. Suppose that you have a look at, you go around and you talk to some of your friends, all right, or on your neighborhood, or your neighbors, and you figure out that many of them were infected by COVID-19. Okay, so you think that the probability that a person in your community has a disease is more than 50%. For example, we talk to 10 people, and then 7 of them were infected by the COVID-19. And then if you say that it is, in your community, it must be more than 50%. Then okay, some people may not agree with that, all right, because they say you get only 10 people, and then you can talk to more people. Let's say you talk to 50 people, right, and you figure out that, let's say 40 of them among 50 people were infected by COVID-19 in the past. Then you say that, okay, you believe that it is, the proportion is more than 50%. Well, some people may argue that this is not really accurate. So what is the point here? How can we make a conclusion? How can you come to a conclusion that all the people can agree? Or is there any reasonable conclusion about that? Is there any reasonable conclusion or reliable conclusion? Is there any reliable conclusion about that? Well, then in that case, you need to come up with the hypothesis testing. Okay, that is what you can do with hypothesis testing. For example, you measure the velocity, and you think the velocity is not 50 centimeters per second. So can we say that it is if that conclusion is true or not? Suppose that you think that you want it to be 50. You want it to be exactly 50 centimeters per second. Okay, but you get something like you get something like 49.9. And then for the average value. So if sometime you can get, let's say you get 49.9, and then 49.8, 50.1, something like that. Or you can say 49.1, 45, 54, okay? So in these two cases, can I say that the velocity is not 50, or can I say that do we have enough evidence to say that it is not 50, or not? So that is what we can do with this. So first of all, you need to know the statistical hypothesis. The statistical hypothesis is just a claim, a statement, a conclusion that you want to make, that you want to test. All right. You may see that H0 and H1, there are two kinds of hypotheses here. S0 is the null hypothesis, and that is the claim you initially assume that it is true. So it is the hypothesis we assume to be true at the beginning. H1, the alternative hypothesis, and sometimes you can see that they denote it by HA. A stands for alternative. So the alternative hypothesis H1 is a claim which is contradicts to the null hypothesis, and it is usually what you want to confirm. Okay, that is usually what you want to confirm. And the test of hypothesis is a method for using sample data to decide whether the null hypothesis should be rejected or not. You know, the hypothesis is about the parameter, about the population. Okay, and the test hypothesis only use the sample. That's the point. All right, the test hypothesis only use a sample. All right, and the null hypothesis, or the alternative hypothesis are about the parameters, the population. Okay. Okay, so here are several kinds of hypotheses you may see. We may get two-sided alternative hypothesis or one-sided alternative hypothesis. H1, if H1 is greater than 50, that is a one-sided alternative hypothesis. Mu is less than 50, that is also a one-sided alternative hypothesis. If it is mu is not 50, then it could be less than 50, or it is greater than 50. So you get two-sided alternative hypothesis. Okay. All right. Concerning the procedure, then you get a procedure leading to a decision about a particular hypothesis is called the test of hypothesis. So so a test of hypothesis is a procedure leading to a decision about a particular hypothesis. And there are two possible conclusions that you can make. You reject the null hypothesis, and you fail to reject that hypothesis. Just like at the beginning, we always assume that the null hypothesis is true. That is what we always do. We assume that the null hypothesis is true, and there are two kinds of conclusions that you can make. You can reject F0, or you fail to reject the null hypothesis. Okay? Is that clear? Is that clear, everybody? Is that clear? Everyone, is that all clear? Okay, and what should we do in this case? So we assume that the hypothesis is true, and if you find something wrong, then we reject it. Okay? If you find something wrong with the calculations, then we reject it. Otherwise, we fail to reject it. Okay? And in order to do that, you need to compute a test statistic. In order to do that, you need to compute a test statistic. So that is simply, you need to, from the sample, you compute something, right? Let's say you have a data, you have a set of data, and then you do something, you have a calculation, let's say this kind of machine, you do some calculation, right? Then you compute a test statistic. without S. We don't have S here, no S, all right? Statistic, and based on this one, if the statistic belongs to the rejection region, then we reject the null hypothesis. If it does not belongs to the rejection region, then we fail to reject. Okay, understand? That makes sense? Is that all clear, everybody? Now, there are two kinds of errors that you can make in this case. There are two kinds of errors that you can make. First, you can see that S0 is true, and then you reject it, then you make an error. If you fail to reject, then you make no error. All right. The null hypothesis is false. It's actually false, and you can reject it, then you make no error. But if you fail to reject when it is false, you make a time 2 error. All right. So there are two kinds of errors here: time 1 error and time 2 error. So basically, a time 1 error consists of rejecting the null hypothesis when it is true, and the time 2 error involves not rejecting the null hypothesis when it is false. Okay. The type 1 error is more serious. It's usually more serious than the time 2 error. That's why in this course we mainly focus on the time 1 error. All right, and the probability that a time 1 error occurs is denoted by alpha, and you call it the significance level. You call it the significance level. Okay, and the probability that you make a time 2 error is denoted by beta. All right, denoted by beta. 1 minus beta is the probability that you can reject the null hypothesis when it is false. It is like you can put a guilty person to jail, right? And you call it the power of the test. Understand? You know, statistics is a kind of applied science. It is not a pure math. Do you know why? Because in statistics, there are several methods that you can use to test one hypothesis. Suppose that I have a claim that the velocity is greater than 50 centimeters per second. That is the alternative hypothesis I have, and S0 is that m is less than or equal to 50. Okay, is that clear? So there are several methods that you can use to test the hypothesis. If you use the first method, then you may not reject it. Okay. So fail to reject. But if you use the second method, you can reject it. Is that clear? So there are kinds of machines, just like in applied science, when you have two methods of measuring. If you use the first method, you can get one value. You use another method, you can get a more accurate value, right? The same thing here. Understand? So maybe today we use this method. We say that we fail to reject the hypothesis, but tomorrow there might be another method which is better, and you can use that method. Then you can conclude that you can reject the null hypothesis. Understand? Okay. So it means that there are many methods that you can use to test one hypothesis, and And how do you know which one is better? Well, you have to compare the power of the test. The method with greater power of the test will be the better method. Do you understand? Is that clear? Okay, that makes sense to you, everybody? Does that make sense? All right. That is basically the main idea of what you want to know about hypothesis testing. Now I want to give you just this example. I'm not going to go over the example, and I will not tell you how to solve the problem. But I will start. I will go over a little bit so that you can understand what I just said. 50 smokers were questioned about the number of hours they sleep each day. It was found that the sample mean is 7.5 hours. And suppose that the population has normal distribution with standard deviation 0.5 hours. Test at the 5% significance level the hypothesis that the smokers need less sleep than the general public, which needs an average of 7.7 hours of sleep. If you have a look at the question, you will see that you know the sample mean, right? You know the sample mean, which is 7.5 hours. You know that the distribution is normal. That is what you know. Okay? And you know that the population standard deviation, right? You know the population standard deviation, which is 0.5 hours. And you want to compare the true average value with 7.7. That is what you want to compare with, what you want to do, right? So you want to know whether the mean value, the mean number of hours that smokers need to sleep every day is less than 7.7. That is what you want, what you think. That is what you think, and that is what you want to confirm. So I have H1, which is that hypothesis. H1, not H0, okay? And then I assume that the null hypothesis, which is M, is greater than or equal to 7.7. I assume that this is true. Okay, I assume that the null hypothesis is true. And if I find something wrong, if I see that the probability that it occurs is really small, then I think that it is not reliable, and I will reject it, and I will support the alternative hypothesis. Do you understand? If the probability that this one, that this fact, this one it could happen, then we fail to reject the null hypothesis, and then we cannot support the alternative hypothesis. Okay, so that is the way we get the null hypothesis, and that is the way we get the alternative hypothesis. Understand? This is very important. If you get it wrong, then the whole thing will be wrong, because you get the starting point wrong, then you will go in the wrong way. Is that all clear, everybody? Is that clear? Okay. All right. I think that's enough for today. Let's stop here, and you may want to check the BK learning for the quiz. All right. The quiz is not about confidence interval. It is about some special distributions, and the deadline for that will be tomorrow noon, 12 o'clock tomorrow. Okay. Any question, everybody? Is that all clear? Okay. All right. Thank you very much. And Welcome back. See you next time. Bye.